section off entitled Trigonometry of Right Triangles. It's right triangle geometry. And I'm going to make two definitions. If here's a person, and here are their eyes, so this is called the line of sight. I guess I'm going to define three things. One is the line of sight. If there's an object up here above the line of sight, then this angle is angle of elevation. This angle right here. If you have to look up, it's called an angle of elevation. If you have to look down, maybe this here is the ground and you're looking at an object on the ground. Or maybe you're looking at an object below the ground, or an object below the horizontal. Below the horizontal. Maybe that's a better name, excuse me. How about we call that the horizontal? I guess your line of sight was this, excuse me. That's the line of sight, and since it's above the horizontal, it makes an angle which is called an angle of elevation. If your line of sight is to this point right here, since it's below the horizontal, we call this angle an angle of depression. From the line of sight, which is straight out, excuse me, maybe I said line of sight, I didn't mean to. From the horizontal, which is, you look straight out, straight across, not up, not down, straight out. Okay, picture that line. If you have to look up to see the object you want to look at, and that object is, say, right here, then we call this angle here angle of elevation. If your line of sight is below the horizontal, that is, you're looking at this object right here. So here's your line of sight. We call the angle that it makes with the horizontal an angle of depression. And that's good to know when you're doing word problems and somebody uses these phrases. I couldn't do any of those problems until I understood what that meant. Okay, so suppose you have this very tall tree. Here it is, the tree, or building. Let's call it a building. You have this building. And you would just love to know how tall the building is. Well, you have two ways to find out how tall the building is. You can go to the top of the building and drop some rope until it hits the ground, and then go and measure the rope. But that involves climbing to the top of the building. Maybe you don't have access to the roof. You have to buy enough rope to go down 100, 10, 20, 30, 100-story building. It can be expensive to buy the rope. And there's really no need to do so. Okay? What you can do is maybe take some kind of a protractor. So here's the ground, and you could put the protractor such that it hits the top of the building at exactly 45 degrees, or 30 degrees, or 20 degrees, or whatever you like. And then what you do need to do is measure this. You have to measure this. Okay? And it's a lot easier to measure this to measure that distance. Okay, and maybe this is 500 feet. So how long is the building? Well, if this is the right angle and this is 45 degrees, then this is the other 45 degrees. Because in a triangle, the angles have to add up to 180. And if this is 90, there's 90 left. And I'm telling you this is 45. So then that's 45. And you should know that two angles of a triangle, whether they're right triangle or not, if two angles of a triangle are equal, then the opposite sides are equal. That is, this length is equal to this length. The problem is done. It's 500 feet. So measuring 45 degrees is real nice. Maybe these days you can find the compass. I meant to say a protractor. Here's the 0, 10 degrees, 20 degrees. Eventually you get 45 degrees. And I suspect you can get one that has a laser beam. And so to redo this problem, here is your building, and here is a special protractor that has a laser beam. You aim it at exactly 45 degrees. And I guess the building should be just a little bit lower. And you put it at that point on the ground, and the laser beam goes right there. And you say, nope, that's not the top of the building. And so you move it a little bit further away. Move it a little bit further away. Again, here's the ground. You move it a little bit further away. Here is 45 degrees right here, or right here if you prefer. And the laser beam goes right to the tip of the building, the top of the building. So now all you have to do is measure that distance. And this distance will be the same. It's a lot easier to do that than to measure a 3,000-foot building or a 100-foot building. How are you going to do that? And now you may say, well, I don't like 45 degrees. Okay. Or possibly you happen to know this information. Suppose here is the building. Here is the building. And here's the ground. Here's the ground. And somebody tells you that this point right here, that's 100 feet from the building. That is, this distance is exactly 100 feet. Okay, so you take your special protractor, I meant to say your protractor, and you adjust it so that the laser beam hits the top of the building, or you use your best judgment with your eyesight, and you read off the angle that's right there. And maybe it's 30 degrees. So now we know that we have this type of triangle. This is 30 degrees, this is 100 degrees, and this is the height of the building. Now, what you want to do is in all trig functions, give the ratio of two sides of the triangle. Well, you're given one, and you want to know the other. I'll call it h for height. Well, which trig function gives you h over 100? Now, h is not the hypotenuse. With respect to 30 degrees, so that's the angle we know, that's the opposite, and the 100 is the adjacent. Well, that's tangent. The tangent of 30 degrees is equal to opposite over adjacent. Well, just like in any fraction, for example, 8 over 4, well, that's 2. 4 times 2 is 8. I'm big on people knowing this. Then you can just say 100 times tangent of 30 degrees. Well, that equals h, which is what we want to know. 100 tangent of 30 degrees is equal to h. You go and you take your calculator and you calculate or compute the tangent of 30 degrees. Tangent of 30, okay, so this is approximately 100 times as a tangent of 30 to, or say 4 decimal places is that number, and 100 times that is 57.74 feet. So now we know the height of the building. It's 57 feet, and we never basically left the ground. Okay, I mean, somebody was nice enough to tell us this distance. We didn't have to measure it. All we had to do was take our protractor and figure out this angle right here, which we computed to be 30 degrees. Now, if they didn't give us the ground, the length from some point on the ground to the building, well, we need to measure off some. Now, I would measure off enough so it's 45 degrees. The problem is maybe the building is really, really tall. And remember, for 45 degrees in a right triangle, the other angle must also be 45. And whatever this distance is, this is going to be the same. Because the building is really, really tall, you're going to have to measure off a long distance. And you may not want to do that. So let's suppose we have this very tall building, and we want to know the height. We have this very, very, very tall building, and we'd love to know the height. So we only go out 50 feet. And since the building is very, very tall, this angle is going to be big. Maybe this angle is 75 degrees. And again, with the with a compass, I was right the first time. With a compass, we can find out this angle. And again, this point here at the very top, that's the top of the building. Okay, so we want to know what h is. H for height. We want to know what this height is. Well, tangent of 75 degrees will be h over 50. Well, this 50 can come up here. That is, h is 50 times the tangent of 75 degrees. And approximately, the tangent of 75 degrees is 3.7321. And when we multiply, so that h is approximately that, because I rounded off this number. And when I multiply this by 50, we get 186.605 feet. So, to a few decimal places, the height of the building is that. Okay, now let's change something. Okay, let's change something. Suppose you are in the building. Here's the ground, and you are in the building. You are on the second floor of the building. And you see another building. See another building right here. You see this building. And you would love to know how tall this building is. Okay, and you're not going to leave your apartment. other than to go out and measure that the buildings are 120 feet apart. You measured that. And now you go back to your apartment and you're not going to leave. Okay, well, here is the horizontal that we talked about earlier. Here's the horizontal. Now, you could find the angle of elevation, and then you can use it to get this distance. And then you can find the angle of depression, because you're looking down, to find this angle. And then you can find that height. Let's suppose you calculated using your compass that this was 30 degrees. And maybe you didn't use your compass, but you protractor. Use your compass. Protractor. You use the one that measures angles. And you measured this one, and you got 60 degrees. Okay, now the question is, let's call this distance 1, or height 1, and we'll call this one height 2. Since I've been using H's, why don't we continue to use H's? So H1 and H2. All right. So let's draw the triangle separately up here. We know this is 30 degrees, and we know that this is 120. If this distance here is 120, then so is this. In both triangles, triangle 1 and triangle 2, it's 120 feet. And we want to know what H1 is. Well, with respect to this angle, we have opposite and adjacent. This tangent, we know that the tangent of 30 degrees is H1 over 120. That is 120 times the tangent of 30 degrees is H1. So, exactly what is the tangent of 30 degrees? Okay, now, when it comes to 30 degrees, we know everything about a 30-degree triangle, a right triangle. We know the opposite angle is 60. So we have 1, 2, square root of 3. So the tangent of 30 degrees is opposite over adjacent. It's 1 over the square root of 3, which is square root of 3 over 3. So we have 120 times square root of 3 over 3. 33, I meant to say, goes into 120 40 times. So we have 40 square root of 3 for H1. That's the exact answer. You want to round it off? Round it off. Personally, I think we should do exact mathematics. Now, let's see where we're going to find H2. So we cut off the top of the building. Okay, now, what we have at this point is we have to look at the second triangle, which looks like this. This here is 60 degrees, this must be 30, right angle. And we want to find H2, and this is 120. Okay, it turns out that we can use tangent again. The tangent of 60 degrees is equal to the opposite divided by the adjacent. But instead of dividing by the adjacent, I can put it on the other side. That is 120 times the tangent of 60 degrees. But the tangent of 60 degrees we can get from here. Tangent is opposite 60. The opposite over adjacent. It's square root of 3. So we have 120 times the square root of 3 is H2. So the final answer, which I'll put down here, is big H, the whole height of the building across the street, is H1 plus H2. And H1 was, okay, I should have equal here. H1 is 40 square root of 3 plus H2, which is 120 square root of 3 plus 120 square root of 3, and that finally gives us 160. 40 plus 120 is 160 square root of 3. So that's the height of the building across the street. And we weren't even on the ground to find that out. That is, you're fine. We measured the distance between the buildings, and then we were on the second floor. We were right here on the second floor, and we still were able to figure out the height of the building. We had to do it twice. And you can find heights of buildings, distance between buildings. For example, if this is one building, and here's the ground, and over here is another building, and you are told that the buildings are, okay, you want to know how far the buildings are apart. Okay, and this time, both buildings are the same height. And this time you were told that this building is 100 feet. And if you were to draw this line, it would be 60 degrees, the angle. Okay, so basically what you have, yes, it'll be a bit shorter or miniaturized, but this is what you have. And somebody's asking you how long that is. How long is D? Okay, now we're going to use the 60-degree triangle because that's given. You can compute this as 30, but maybe you made a little mistake. Why not use what you're given? Maybe when you did 90 minus 60, you got 20, which would be wrong. But there's no way we're wrong if we say that angle and use that angle as 60 degrees. It was given. Now, with respect to this angle, we are the 60-degree angles. We are given their opposite and their adjacent. But I would love to have the unknown on the top. That is, this here is with respect to 60 degrees. This is their adjacent, and this is the opposite. But you know what? That's cotangent. That's the cotangent of 60 degrees. 100 times the cotangent of 60 gives us D. D is 100 times the cotangent of 60 degrees. Now so now 60 degrees is a good triangle because we know about 60 degrees. This is 1, this is 2, this is square root of 3. So the cotangent of 60 degrees is adjacent over the opposite. It's 1 over square root of 3. So we have 100 times 1 over square root of 3. But 1 over square root of 3 is square root of 3 over 3. Final answers should not have radicals in the denominator. So our final answer is 100 times the square root of 3 divided by 3. That is your exact answer. Done. Finished. Exact. So you don't always have to be given the ground distance Okay, one more problem. Well, let's do another problem. All right. Suppose, so here's the building. Here's the building. And the building, you know, is 100 feet. And you take a ladder that's 120 feet. You take a ladder that's 120 feet. Okay, and you know that this angle is 50 degrees. You know that angle is 50 degrees. And somebody asks you, oh, how far did you put the ladder away from the building? It's very urgent that you give them this answer. It's very, very urgent that they give you this answer, that you give them this answer. You have a 120-foot ladder. It goes to the very, very top of the building. And you know that the building's 100 feet long, and you put it at a 50-degree angle. And you're asked, well, how far did you put it from the building? Now, there's two options. You can go out and measure that distance, or you can say, you know what, I'm going to use trigonometry. I'm going to use trigonometry. Actually, you know what, you're not even told the angle. You're not even told the angle. Okay? Well, call this distance x. This is a right triangle. X squared plus 100 squared equals to 120 squared. Now, if you wanted to be slick, you could scale down the triangle. You can divide all sides by 10. And you can say x squared plus 10 squared is 12 squared. And just for the record, if it turned out that x was 6, well then your x here would be 60. It will be 10 times. Okay, so bringing the 10 squared to the other side, x squared is 12 squared minus 10 squared. It's 144 minus 100. It's 44. So then x is the square root of 44. So your x will be 10 times that. It will be 10 times the square root of 44. I'm dealing with much smaller numbers. You don't like that? Fine. Bring the 100 squared over. So x squared is 120 squared minus 100 squared. And you have to know what 120 squared is. It's 14400 minus 100 squared can be 1 followed by 4 zeros. And when you subtract these, you get 4,400. So let me come to the top, please. So if that's what x squared is, if x squared is that, well then x must be the square root of 4,400. But 4,400 is 100 times 44. So since you have the square root of 4,400, you can take the square root of 100 and the square root of 44 and multiply them together. And the square root of 100 is 10, and the square root of 44 I don't know. So we got the same answers. Okay, I had that a while ago. And all I did was sit down with a pencil and paper and I calculated. I didn't go out and measure this distance. And you know what? If you measured this distance, you would not have gotten the right answer. You would not have said, oh, it's exactly 10 times the square root of 44 feet. You would not have said that. What you might have said is using a calculator we can approximate it. The square root of 44 is about 6.6. Multiply this by 10, you would say something like 66.33 feet. But if you really wanted to know the exact answer, there it is. That's the exact answer. I didn't go out, didn't get my hands dirty measuring the ground. You don't see me playing on the ground. Okay, one last thing I thought of about how you could derive that triangle, the 30, 60, 90 degree triangle. If this is an equilateral triangle, that is, all angles are the same, and let's suppose each side is 2. Well, I'm going to cut this in half. That is, this angle on top, I'm going to cut it straight down the middle, the right angle. That means this angle is now 30 degrees. And this angle is still 60. We didn't touch it. This side, this distance is still 2. But this distance was cut in half. It used to be 2, but this is a perpendicular bisector. It cut it in half. So now this is 1. That is, we now have the left half of this triangle. I just drew it. It's 60 degrees, 30 degrees, the right angle. This is 1, this is 2. Pythagoras would come along and conclude that's 3. Because if I called it y for a moment, I know that 1 squared plus y squared is equal to 2 squared. 1 squared is 1. Y squared I don't know. 2 squared is 4. This must be 3. 1 plus 3 is 4. Y squared must be 3. So then y is plus or minus the square root of 3. But since it's the length of a side of a triangle, it's positive square root of 3, which is what I put down. Okay, that finishes this section. Don't get your hands dirty. Use trigonometry.